Hello and welcome to the first video in a course on Galois Theory. In this course, I plan to cover the material you'd see in an undergraduate course on Galois Theory. I expect that the audience have some little background in ring theory and group theory, but nothing much is assumed from the audience as I'll be developing the theory. I'll be developing namely field theory and whatever we need about polynomial rings and so on. In the first few videos, I'll be discussing field theory, as I mentioned, and I'll be reviewing some concepts from ring theory before we get into the core of Galois theory. Just a comment here regarding the organization of these lectures. If you've been seeing my videos, you might have noticed that I have this new style where I'm using some slide as a reference. However, I should insist that I should mention clearly that I'll be writing proofs. I'll be writing proofs by pen as we go in the lectures. If you feel that there is some background in abstract algebra that is missing, you can refer to my course on abstract algebra, which is also available on my channel. So before we begin, let me just before we begin our first lecture on field theory, on a review of field theory, let me just give you a rough idea of what's going on in Galois theory. So broadly speaking, Galois theory is the intersection of field theory and group theory. So what Galois theory does is that it takes questions from field theory and it kind of translates them or finds an equivalent problem to them in group theory, which makes life easier most of the time. So the theory was developed by the mathematician Galois, who had a hard life. So Galois' original question was, he was faced with this question that so we know that for a quadratic polynomial of the form ax squared plus bx plus c, we have the roots minus b plus or minus the square root of the discriminant, which is b squared minus 4ac over 2a, right? So this polynomial has like this compact form of the roots, and Galois' question was, say we take a fifth, or like a polynomial of degree 5, right? So if we take a polynomial p of x and this is of degree 5, so can we find a solution to can we find can we express the roots of this polynomial in a compact form in terms of these arithmetic operations that we know, and possibly some radicals? So this question is a hard one, and it was answered by Galois by relating the roots of these polynomials to a group known as the Galois group. So for example, for the polynomial x to the 5 minus 1, you do have some like the roots are the roots of unity, right? So these are the roots on the unit circle that forms a fifth-sided polygon, right? So some of these polynomials do have solution in terms of radicals and the usual arithmetic operations, but some other don't, right? And this question was answered by Galois at his age of 18. Like, he was only 18. This was in 1830. So Galois answered in his memoir. He published a paper about the solvability by radicals of like finding the roots of polynomials by radicals. He published his paper in around 1830. But his paper was rejected. So his paper was rejected, ironically, because he kind of provided sketches of proofs. So he was kind of sketchy in his proofs. So it was rejected, I think, in 1831. And later on, another mathematician came and figured out this work, and he kind of completed the work with some explanations, and he of course gave credit to Galois. His name is Liouville. So this other mathematician was the one who revealed the work of Galois. So I should mention that the problem of solving a polynomial by radical was tackled by the mathematicians Abel and Ruffini. However, mathematicians claim that the work of Galois kind of supersedes the work of Abel and Ruffini. So this is a kind of rough idea of what's going on in the theory. So I hope that this was a little motivation of what's happening in the theory, and I'll be motivating things as we go, but we need some background before we do some explicit motivation of what's going on. So our first lecture is gonna be about field theory and some properties of fields. So let us start here. So let us start off by defining what a field is. So I remind you, a ring is a set R with two operations, where if you take R with plus, you have a group, and if you take R with the multiplication, you have a monoid. So a monoid is just like a group, but the elements don't have inverses. So a ring is just a set with two operations, addition and multiplication, where if you consider R with the plus, you get a group. You more specifically get an abelian group. And if you consider R with the multiplication, you get a monoid, which is a group, except that you don't have inverses for the elements. And I should mention here an important definition. So this is our first definition in the course. This is something that I assume the audience know. It's fine. I'll be sketching some important definitions as we go. So this is a group without this is some wavy definition. This is a group without inverses. And we also require that the addition and the multiplication are distributive. Alright, so I should mention two important things here for the audience to keep in mind. First of all, I would like you to kind of grab a piece of paper and put on the side whatever tricks, whatever important definitions, whatever important notes I give throughout these lectures. And here are some of the things I want you to pay attention to. First of all, so some people define the ring as a commutative ring. However, here in our definition, it's not necessarily that the case that this ring is commutative. And in other words, the multiplication is not necessarily commutative here. Right? It's not necessarily the case that A dot B is equals to B dot A for B and A in R. So this is the one thing I want to mention. And the other thing I want to mention is another important definition over here that I need to sketch before we define what a field is, which is that elements of the ring of a ring are that have multiplicative inverses are called units. So this is an important definition for you to keep in mind, and I stress here we're talking about multiplicative inverses, right? Because already over addition, R is a group, which means every element has an additive inverse. However, over the multiplication operation, it's a monoid, it's not a group, so not every element has an inverse. However, if an element has an inverse, we call it a unit of the ring. Alright, so let us start by defining what a field is, and we'll be giving some examples. Alright, so if we want to define what a field is in simple terms, well, a field F is just an abelian group. So it's a ring to start with. A field is a ring, so F is a ring, and which means it has two operations, addition and multiplication. And what we require is that, since it's a ring, we know that over addition it forms an abelian group. We require that it's an abelian group, which means it's a commutative group. And the other thing that we require is that we require that F take away 0. So if we take away 0 from F, we require this to be an abelian group. And this is a very important thing. So because this is saying two things, actually. This is saying two additional things that a ring doesn't have. Well, the first thing it's saying is that so it's saying that it's a commutative ring, meaning it's an abelian group over multiplication. Meaning if you take any two elements in F, A dot B is going to be equal to B dot A, which is not the case for general rings unless the ring is commutative. Commutative over here. So this is the first additional thing that a field has that a ring doesn't. And the other additional thing is that it is a group and it's no longer a monoid. And what we mean here is that every element of the field is a unit. And to state this differently, every element of F has a multiplicative inverse. And this is very important. It literally means that every element of the field F is actually a unit, right? So for every A in F, we require that there exists a B where A dot B is equal to 1, since we're talking about multiplicative inverses here. And we usually denote B here, we usually denote it by A inverse as such. Since the field is commutative, we will also have that this is the same as BA. So these are two additional things that a field has that a ring doesn't generally have. So these are the two things. And also, since it's a ring, we have that multiplication is distributive over addition. So this is something that we require. So I hope that this definition is clear. We're gonna state it differently. We can state it differently, but if we want to write out what the properties are, what does it take for f with the addition to be an abelian group? What does it take with f take away 0 with the multiplication to be a group? What does it take for it to be distributive over addition? Here are the properties. Here are the field's properties, right? First of all, for it to be an abelian group, what we require is that over addition, we require closure under addition. We require the operation addition to be a binary operator. I remind you what that means is that we require closure under addition. If we take any two elements, it has to add up to an element in the field. And the other thing that we require is commutativity, because we have that it's an abelian group. So it's an abelian group over addition. So here we're talking about f with addition in these first few properties. We also require associativity, because this is one property that makes a group, and we require the existence of an additive identity. Also, this is one important characterization of what a group is. We require additive inverses, and this is also an additional property for f with addition to be a group, right? So I'm going over these real quick because I'm assuming that the audience is familiar with what a group is, right? So a group is a set with an operation, right? That is where the operation is binary, meaning the set is closed under that operation, and we require associativity, existence of additive identity, and existence of additive inverse for every element. And since the group is abelian here, we're requiring commutativity of the operation. So this is what makes f with plus an abelian group. So this is what makes it an abelian group, like f with the addition. And we also require that f take away 0 is a group under multiplication. So we also require these for, like, these are these properties. So this would make f take away 0 with the multiplication an abelian group. Again, we require associativity of the multiplication. We require the existence of multiplicative identity and the existence of multiplicative inverses. And we also, since it's an abelian group, we require commutativity over the operation. And since it's a group, we're gonna require that the operation multiplication is binary, meaning that there's a closure under the multiplication, and finally we require that it's distributive. However, two important notes here, or one important note. We are calling, this is an important thing here, we call the additive identity zero, or we denote it by 0, right? This is important, right? So we're denoting the additive identity of the field by 0, and we denote the multiplicative identity by 1, right? We're gonna take some examples now, but let me just state these important things. What else? The other important note that I wanted to make is that we're denoting multiplicative inverses by a to the negative 1. So this notation we'll be using over and over again. This is why I'm stressing it right here. So multiplicative inverses are denoted like this, right? This is how they're denoted. And what else? Additive inverses are denoted as such. Additive inverses are denoted as such. All right. So this is what makes a set with two operations. This is what makes a set F with two operations a field. right? So now that we've defined what a field is, let us take some examples. Here are some examples of fields, and these are important examples because these will be appearing over and over again in the theory, in Galois theory, and these are important examples of fields to keep in mind, to keep in your pocket to use whenever a question comes. The rational numbers, if you take the rational numbers with the usual addition and multiplication, this forms a field. Well, it is obvious that Q with addition is a group. It's an abelian group, right? And it's obvious that Q, if we take away 0 and we look at the multiplication, it's also obvious that this is an abelian group. But let's see why. Well, elements of Q are of the form A over B. Now, if this is not 0, right, then it has an inverse. What's the inverse? A over B inverse, because remember, this is how we're denoting multiplicative inverses. We take the element and we write -1 above it to denote the multiplicative inverses. Well, what's the inverse? It's actually B over A, and we can do that because this is not 0, right? So we're taking away 0 so that we can do that. And remember, one important property is that the inverse should remain in Q, right? And it's also obvious, right? It's also clear that the addition and multiplication are distributive, right? And this is what takes for Q with plus and the multiplication operations, the usual ones that we know. So these are the rational numbers. This is the set of A over B, such that A and B are integers, right? So this is the set of rational numbers. As you see, you can refer to my course on abstract algebra to see proofs of why these are abelian groups. But I expect that these are easy things to verify. But you can still refer to my videos. I'm gonna put them at the end of the video to see for example, proofs of these in details. And in a similar fashion, one can see that the real numbers with addition and the multiplication that we know is also a field, right? The complex numbers with addition and multiplication is also a field, right? So these are the easy examples, I would say. If we want to go a little bit harder and see what's going and see a little bit harder example of what of fields, let's look at this field, right? So let me tell you what this field is. So let's talk about number 4, because number 4 is one of the very important examples of fields, and in fact this is called the algebraic extension of Q. So we take the rational numbers and we extend it by square root of D. The terminology here is that we adjoin square root of D to Q. This is the terminology that we'll be using, and a lot of Galois theory is in fact about extensions of fields, as we will see in the coming videos. But I'm just trying to throw some terms here. So what is this field? Well, this field is, as a set, it's the set of all numbers a plus b square root of d, such that a and b are integers, right? And what we require usually that d is square free. let me just say not square, let me say it's not a perfect square. Perfect square. And what that means is that we require that d is not n squared, is not some number that is some number squared, because in that case adjoining d would mean nothing, right? Because the square root of d in that case would be just n, right? And if this is n, then this set, like, it's gonna be literally q, right? There won't be any additional things. However, let me give you an example here of such a field before we prove that there is actually a field. So let us see here. Q square root of d. Let's take d to be 2, for example. Square root of 2. 2 is not a perfect square, so we can take this. So if we look at this for a, b integers, let's see why this is a field, right? Let's see why this is a field and what we're really doing. So what we're really doing here is that we're kind of introducing a new basis vector. So if you look at this closely, you see that we have a basis 1 and the square root of 2, right? Because we're taking linear combinations of 1, right? There's a 1 here, right? And the square root of 2. We're taking excuse me, that this is in Q, right? It's not in Z. This is in Q, right? So because we're talking about the rational numbers here, we're adjoining the rational numbers. One important thing here is that this is a base, like the basis that we're taking, like we had a basis that is just 1, and now we're taking the basis that is 1 and square root of 2. And why is this a field? It's important to see the proofs at least once in your life. So I'm gonna go over this. So it might be an elementary check for some people, but I expect some audience haven't seen this. So I'm gonna go over this real quick. So let us prove that. So here's the proposition that we're proving. Q square root of 2 is a field. So before we prove that, I'll tell you that the proof of Q square root of D adjoining square root of D would be similar, right? It's gonna be a little bit of just a little modification of this proof, and it'll prove it in general. So let us see why this is the case. Why is it a field, right? So before I tell you like why this is a field, I should tell you what exactly I mean by that. I should tell you what's the addition and the multiplication here, right? So we're defining, so what we're gonna do is that we're gonna take, so this is a generic element of Q square root of 2. We're gonna define the addition of two such elements, say a prime plus b prime square root of 2. We're gonna define this as a plus a prime, like we're gonna do the usual thing. We're gonna add the terms that are similar to each others, and we're gonna define this as b plus b prime square root of 2, right? So this is how we're defining addition. And how will we define multiplication? We're gonna also do it in the usual sense, right? We're gonna just do it in the usual form, like in the way you would expect it, right? How would we multiply two such elements? Well, what we'll do is that we'll just expand this, right? We're gonna define this by the expansion of this thingy. It's gonna be as such, like if you multiply this out, it's gonna take the form a prime plus b prime, and there's a 2 here because you're multiplying square root of 2 and square root of 2, and then you're gonna have the other term is a b prime plus b a prime times all of this times the square root of 2. So what we're really doing is just expanding, right? We're just expanding this and writing things in the form of in the form of the elements of q square root of 2. So the first two properties that we just checked is that these two operations are binary, meaning that the set is closed under these operations, right? So this is also in q square root of 2, and this is also in q square root of 2. I hope that you agree with me. Alright, so the other properties, such as the existence of, such as associativity. So what we want to prove that this is a field, we want to prove that q square root of 2 with addition is an abelian group, right? And we want to prove that q square root of 2 with multiplication, if we take away 0 with multiplication, it's also an abelian group. And we want to prove distributivity of the addition and multiplication. Okay, so now that we have a set with two operations that are binary operations, so let me just denote these. This is 1, 2, 3. So proving 1 would be easy. I'm gonna assume, like, associativity, I'm gonna leave it as an exercise for you. It's an easy thing to check. The identity, what's the identity? It's important to mention these once in life. What's the identity here? And it's important to note that we're talking about additive identity, which we said we're gonna denote it by 0. Well, fortunately, in this case, 0 is literally 0. Like the 0, the identity 0 is literally the 0 of q, right? So this is when we take a equals b equals 0, in here we get the 0, right? And you can check that it satisfies the additive identity property, that when you add it to any other element of this form, you get the same thing, because this is how we're defining addition, right? This is how we're defining addition of two elements. If this is 0 and this is 0, like, the element won't change, right? The other thing that I wanted to mention here is the inverses. What would an inverse, so for every a plus b square root of 2 and q square root of 2, what's the inverse of that? Well, the inverse is negative a negative b square root of 2. Right, so this is the inverse. It's the obvious, right? Because this is how we're defining addition. So you expect that this, like, you should take a prime such that this cancels out and this cancels out. So this is the inverse. And what else do we need to check? So this checks 1. To check 2, you'd also do similar things, like associativity exercise for you. Identity, what's the identity here? It's important to stress that it's called multiplicative identity. What's the multiplicative identity, which we said we're going to denote it by 1? What's our 1 here? What number would we get? What number of q square root of 2, which when we multiply it by any number of this form, we get this same number back? What would that number be? Well, fortunately, in this case, it's an easy thing. It's also 1. But how would we write it as an element of q square root of 2? Well, it is 1 plus 0 times square root of 2. This is an element of q square root of 2. So the other important thing is the inverses. So here in 2, we're trying to prove that q square root of 2 take away 0 over multiplication. It's an abelian group. And by the way, I should mention here that commutativity over addition is also clear, right? Because this is how we're defining addition. And certainly a and a prime here commutes, b and b prime here commutes, and thus the addition of two such elements commute, which makes this not only a group but also an abelian group. So inverses, if you take an element, this is important just to mention it at least once in life. What's the inverse of a plus b square root of 2? when this is not 0. Why is this not 0? Because we're talking about elements of q square root of 2 take away 0. So we're assuming a priori that this element is not 0, meaning one of a and b is not 0. So how would you take the inverse of this? Well, since this is not 0, you know that this is a real number that's not 0. So you know that the inverse is this thing. But the question is, why is this element in q square root of 2? Why? Like, we do know that this is the inverse of this. We know that if we multiply these two, we get back 1, which is the identity in our group, right? But the question here is that why is it the case that so why is it the case that this is an element of q square root of 2? Is it clear? Is it clear from just looking at this? Well, it is, because you can just do the usual rationalization trick. So you can just rationalize this thing, and you get the form that you're looking for. If you do this computation, you will get a over a squared minus b squared. There's a 2 here, and minus b over a squared minus b squared, and there's also a 2 here, and there's a square root of 2. So this is also in q, and this is also in q. Thus this whole thing is in q square root of 2 take away 0. And it's gonna be not 0, obviously, because if this is not 0, there is no way this can be 0, right? So so inverses do exist in this group too, and commutativity, it's also obvious from the way we're defining this multiplication of two elements, right? So it's obvious that if we just interchange the roles of a and a prime, b and b prime, that we get the same thing. So commutativity is also obvious. So it's also an abelian group. So it's also the case that q square root of 2 take away 0 is an abelian group. All right. And for the third thing that we need to check, which is distributivity of addition and multiplication, this is an easy exercise for you. So exercise, prove distributivity of addition and multiplication. Right, so this is an easy exercise for you guys. So all of this, this might be a tedious thing to do, and it might be, however, it's important to see it once in life. It's important to see why such a thing is a group, right? It's important to see it once in life. So the other thing that the other important example of a field that I want to mention for you is what's so-called FP. Right, so where p is a prime. So let me just mention this real quick too. So this is the other example, FP, where p is a prime. And I remind you here by FP, what we mean is that we mean z modulo pz, right? So it's the set of all elements. It's the set of reduced residues modulo p, meaning it's all of these numbers modulo p. And we're defining addition like we define a plus b. If these are two elements in here, to be we're defining this to be a plus b modulo p, and we're defining a times b to be a times b modulo p. All right, so we're talking about FP with this addition and this multiplication, right? So these are this is the field that we're talking about. Why is it a field when P is a prime? Well, I expect you to have seen this, that this is a ring. So I expect that you have seen that this is a ring, and it's obvious that if you multiply any two elements in here in whatever order you want, you also like the multiplication is commutative, so this is a commutative ring, right? So why is it a field? It suffices to tell you why every element of this set has an inverse, has a multiplicative inverse, and this will complete the proof of why it is a field. Well, if you take any element, let's take an n in Z mod PZ, right? So n is between 0 and P, right? Alright, and since we're interested in multiplicative inverses, we'll be looking at Z mod PZ take away 0. So we'll be interested in elements that are non-zero. So it's strictly between 0 and P, right? So why does an inverse exist to such an element? Well, since P is a prime, any element less than P has a GCD. So the GCD of P and N is 1, and by Bezout theorem, you know that there exists an A and B integers such that AP plus BN is equal to 1. But since we're working in Z mod PZ, then this whole thing modulo P is going to be just Bn, and thus you've just found an inverse of N, right? You've just found an inverse, namely N inverse in this case is B. So whenever N is not 0, it has a multiplicative inverse, and this what proves that FP is a field. So in the coming video, we'll be covering more properties of fields, but we'll be going at a faster pace. Just wanted to give the definition. I just wanted to give the definition its time so that you grasp the definition well before we start doing some denser things. So in the next video, we'll be covering the rest of the important properties needed from field theory, and we'll be transitioning to other important topics.